Welcome to the deep dive. Today, we're really pulling back the curtain on some unseen experts in healthcare. These are the qualified medical physics specialists, the QMPS, our mission, to explore how these, risk managers connect fundamental physics and advanced engineering right to your care.
That's right. And their role, it really stands on three legs: clinical service, R&D, and teaching. But fundamentally, the QMPS mandate is ensuring the safe and effective use of physical agents, especially radiation, they're translators basically, taking complex physics and turning it into a safe, personalized treatment plan, all while managing critical safety aspects like radiation protection, shielding and all that.
Okay, so that's the groundwork. Let's dive into diagnostics because how we see inside the body is changing dramatically. We're talking hyper-resolution imaging. First up, photon counting CT, PCD-CT. This sounds like a pretty big shift from standard CT detectors.
Oh, it absolutely is a total paradigm shift. The data complexity just explodes. PCD-CT literally counts single photons. This gives us ultra-high resolution, think clarity down to 0.2 millimeters. And crucially, it delivers always-on spectral information.
Spectral information,
Yeah.
so not just density, but what things are actually made of, chemically.
Exactly. You're seeing the tissue's chemical makeup. It's incredibly powerful information.
And where did that pay off immediately? What's the big win?
Cardiology, hands down. We're seeing huge improvements in visualizing tiny vessels, checking if stents are clear, and maybe most importantly, it avoids those blooming artifacts from calcium that often hide important details in conventional CT.
Okay, that kind of seeing really sets the stage for the next jump. 7 Tesla MRI. Ultra-high field, so you crank up the magnetic field, you boost the signal to noise. But going to 7T, what's the trade-off? Is it longer scans, more difficult for patients? What do we give up for that sharper image?
Well, yeah, that's a fair point. It definitely requires specialized training, very optimized protocols. It's not just plug and play. But the images, they're worth it. If 3T is standard definition TV, 7T is like jumping straight to 8K. You see the pixels of the disease, so to speak. Take neuroimaging, like in multiple sclerosis, lesions that look like one big blob on a 3T scan. At 7T, you often see they're actually multiple distinct small lesions. And that detail, it makes it invaluable for really precise surgical guidance. Things like deep brain stimulation targeting. Precision is key there.
Right, and that precision imaging needs precision treatment to match. Let's talk therapeutics. Theranostics. Yeah. This idea of integrating diagnosis and therapy with these super-specific radio tracers, pushing towards targeting on a nanometer scale.
Absolutely. We're moving beyond just shaping radiation beams geometrically. We're now targeting things molecularly. And the next generation is really exemplified by isotopes like terbium-161.
Text-2. What makes it such a potential game changer compared to, say, lutetium-177, which is used now?
It's the physics, the way it actually kills the cell. Textape releases these things called auger electrons, highly cytotoxic. Think of them like tiny, tiny depth charges. They only travel nanometers, like the width of a few molecules, and they deposit their energy right beside the cell nucleus.
So extremely localized damage.
Exactly. Intense energy deposition causing devastating DNA damage, but only over incredibly short distances. It's a high-lit particle effect. Lutetium-177 works well, but its electrons travel further. Texam offers this potential for really intense, focused cell killing right where you need it, sparing more healthy tissue nearby.
All this amazing data, this therapeutic precision, it sounds incredibly complex to manage. Which brings us to the human bottleneck, right? All this complexity, the hyper-res images, intricate dose plans, it feels like it almost demands artificial intelligence, the AI imperative.
It truly is mandatory now. Yeah. AI tools are absolutely crucial for automating tasks. Basic things like outlining organs or tumors on scans, image segmentation, and it's essential for enabling the kind of high-throughput workflows you need for things like adaptive radiotherapy, RT.
RT. That's where you adjust the treatment plan almost in real time, day to day.
Exactly. Modifying plans based on changes in the patient's anatomy or tumor response. Without AI handling the data crunching and plan adjustments quickly, that level of personalization just isn't feasible at scale. It's too complex.
But here's a crucial point. If we're developing these incredibly advanced and likely expensive solutions, are we accidentally creating a two-tiered system where only the big, well-funded centers can actually afford to implement them?
That hits on the most critical systemic challenge: access. You're absolutely right. The high capital cost of, say, a particle therapy center or a 7T MRI system, it definitely risks making existing health inequalities worse. widening that digital divide. We need to be mindful that these amazing personalized and precision treatments don't just become tools for the privileged few.
So the diagnostic image isn't just a picture anymore. It's become this quantitative biomarker that's actively driving therapy decisions. The stakes are higher.
Absolutely. And that signals a huge shift for the future workforce, too. For the QMPS, education has to evolve. It needs to emphasize deep skills in advanced computing, managing huge amounts of information, data analytics. You need those skills to effectively handle these integrated AI-driven hybrid systems that are coming online. It's a whole new ballgame.